but I think this is going to be a nice talk to kind of tie things together. Either after this, depending on the discussion, or tomorrow, I think we're going to kind of roll up the sleeves and talk about what some of the real issues are in trying to implement something or performing an experiment to talk about really the sort of big elephant and gorilla in the room today about enhancing upwelling and growing fish. So maybe we'll get more direct about that after this talk. And one of the things Ken's going to talk about really is location and how places in the world might be a factor in determining where you would do this.
Okay, so I'm going to start with these little quotes. And Walt Whitman in the book of poetry on Leaves of Grass had a comment that after looking out and seeing the cattle grazing on the great fields or grasslands of America, he made that comment that flesh is grass. It's also a biblical saying, too. Henry Bigelow, one of the famous fisheries oceanographers, has made the comment that fish is diatoms. I'm a firm believer of that. I know Dick Dugdale's a firm believer of that.
I've used that one many times.
Okay. And I'm going to show you here that diatoms are nitrogen, phosphorus, silicon, and iron.
And a few other things.
And a few other things. But these are the key things that are and in fact, well, carbon's not limiting that to the same extent as nitrogen, silicon, and iron are to diatoms.
You're not in the poetry department today.
So what I'm going to give is really three things, a really brief big picture overview of iron versus nutrients such as nitrate, and sort of why can iron be limiting, and I'm going to give you a really simple tutorial on that. And then a brief overview of our group's research efforts in the coastal upwelling waters, particularly off central and northern California, and the role of iron in phytoplankton blooms. And then I threw in a few slides of overview of importance of eastern boundaries of oceans, particularly eastern boundary of the Pacific, that would be the place, as far as I'm concerned, where you would want to try and induce upwelling and induce higher productivity. So here's your vertical distributions of the nutrients: nitrate, phosphate, and silicic acid. You've got the phytoplankton assimilation in the surface waters. You've got the export of some of this material. It's the remineralization through the oxidation of this organic matter by respiration for nitrate and phosphate, and then just the dissolution of the silica, the opal carrier phase for silicic acid. And all I wanted to do was point out that the majority of all the export of organic matter falling into the deep sea is remineralized back to nitrate and phosphate. The vast majority of all the opal that falls into the deep sea is remineralized back to silicic acid. And then these things, I'll just point right here, if you bring that to the surface by vertical mixing or upwelling, you're bringing that bag of fertilizer back to the surface, you're bringing that phosphate back, you're bringing that silicic acid back, just in about the perfect ratio that they're needed for diatom blooms to take place. So it's a perfect place. You don't have to add any other thing, you've got it. Now, if you look at a trace element like zinc, what you see, okay, and what I've got here is I just plotted here to show you the zinc silicic acid distribution in the North Pacific and the North Atlantic. And you see what Francisco Chavez was talking about earlier, that the young deep waters of the North Atlantic are very poor in silica. It hasn't had the chance to build up in concentration. The old deep waters of the North Pacific have built up to where you've got really elevated silicic acid concentrations. So the Pacific is your nutrient-rich ocean that you want to think about. And then you can look at some trace elements that are what we call nutrient type. And zinc is a classic nutrient type trace element. And the majority of all of the zinc that is assimilated in the surface waters falls out into the deep sea with biogenic particulate material, is remineralized, resolubilized in the deep ocean, just like the nitrate, the phosphate, and the silicic acid is. And you got the zinc coming back in here. And if you look at that zinc here, bringing back to the surface, it's almost just the right amount of zinc that you need in order to get a new diatom bloom or a new phytoplankton bloom. The problem comes with iron. And here now is a nitrate distribution in the Pacific versus the Atlantic. And here's a dissolved iron distribution in the Pacific versus the Atlantic. Now, at first glance, this is the very first data that John Martin ever put together. And at first glance, you see, wow, that looks just like a nutrient distribution. It's depleted in the surface and rich at depth. But what happens with iron is that in the deep ocean, it's being scavenged out or removed onto particles in the deep ocean with about a 200 to 300 year residence time in the deep sea. So during this 1,000-year transit time from the North Atlantic to the North Pacific, all along that transit time where nitrate's building up, silicic acid's building up, phosphate's building up, zinc is building up, iron's being stripped out. And by coincidence, the remineralization of iron, it just about balances the scavenging of iron. But the net result is that 80% of the iron has been stripped out of the ocean during this transit time. And now when you upwell that iron back into the surface along with the nitrate, there's not nearly enough iron to go along with the phosphate, to go along with the nitrate, to go along with the silicate. And in fact, if you upwell this 25 to 30 micromolar nitrate with only 0.2 of a nanomole of iron, you very quickly drive the system into iron limitation, and you end up with these low chlorophyll, high nutrient regimes, these HNLC regimes in the ocean. And if you look, here's a model that Jefferson Keith Moore at UC Irvine put together in 2004. A computer model where he's put all these different factors, the physics, the biology, and the chemistry of the oceans together. And he looks at diatom growth limitation and looks at these different parts of the ocean. The majority of the ocean is limited by nitrate, okay? The oceans, the majority of the, these are these major subtropical gyres of the North Pacific, the South Pacific, the South Atlantic, the North Atlantic. The majority of the oceans are limited by nitrate. And especially because we've driven out the Arctic and driven out the Antarctic part in this sort of map. We're overemphasizing the Antarctic and the Southern Ocean here. But what I want to show you, though, is that in these areas, the subarctic Pacific is an area where it's an upwelling gyre where we're bringing nitrate, phosphate, silicic acid to the surface at high rates. Those are areas that we're just not bringing enough iron with, and it becomes iron limited. The equatorial Pacific, where due to the divergence along here, we're upwelling water to the surface. We're upwelling the nitrate, the phosphate, the silicic acid, but we're not upwelling enough iron with it. And the same with the Southern Ocean, the entire Southern Ocean, where we've got that tremendous vertical mixing because of cold. Again, we're just not upwelling enough iron. So you've got, in this case, this model, they have 28% of the world's oceans is limited by iron. 56% of the world's oceans is limited by nitrate. And you can even see a little area over here off the Sahara Desert where you get all that dust, iron coming from the Sahara Desert that even has become phosphate limited. And then Dick Dugdale loves this because here's this yellow area, this silicic acid limited, okay?
Yep.
Yep, okay.
I could have a little bit more yellow there too.
Yeah. But one thing that the physics of Keith Moore's model still doesn't, do a very good job at all is with coastal upwelling regimes. And so you don't see the upwelling regimes along California. You see the upwelling regime along Peru, but it's more tied into this equatorial regime that Francisco talked about earlier today. And you don't see the upwelling regimes, across here. So it doesn't do a good job with coastal upwelling. Okay, that's a major limitation. Okay, so now so that's your brief tutorial on iron and why iron would be important. It's not being remineralized, resolubilized like all of these other things. And so if you just have upwelling, you're not bringing enough. And in order to bloom, I put these here off of California now. And I think the same thing would be for off of Peru, that by far the most critical nutrient here is nitrogen as far as being limiting, and then for the micronutrients would be iron. And this next figure sort of shows that. Turns out that Liebig limitation is more important than sort of the growth rate limitation. But Liebig limitation is what is that nutrient that's going to end up limiting the final biomass that you can get. Liebig was a famous agricultural chemist in the 2 centuries ago, whatever, anyway, a long time ago, and he grew corn crops and things like this, and he discovered what was the limiting nutrient that would limit that crop. And if we look at the limiting nutrient that would limit a diatom bloom, I'll talk about 30 micromolar nitrate upwelling into the surface waters, going to 0 micromolar nitrate in the bloom. That bloom produces 30 micromolar of particulate organic nitrogen, about 30 micrograms per liter of chlorophyll, about 33 micromolar of biogenic silica, and about 200 micromolar of particulate organic carbon. So this is just Redfield stoichiometry you got here, together with sort of Brzezinski silica stoichiometry. And then if you look down here Together with that 30 micromolar nitrate, coastal diatoms require phosphate. They require 1.9 micromolar to go along with the 30 nitrogen. Present in upwell water, 2.2. Okay? In off Peru, off California, you're not going to see the phosphate limited. It's going to be nitrate limited before phosphorus is limited. Unlike some of the other areas like off in the Gulf of Mexico or something like that Hans talked about earlier today. Silicic acid, you need 33. There's 30 to 50. It's generally not limited, but you can go to the edges of these areas and find the system's silicic acid limited. Iron, depending upon the value used, you need about 6 nanomole of iron to go along with that 30 micromolar. What you have, if it's offshore upwelling, you've got 0.5. If it's upwelling over a shelf, like I'm going to show you in a little bit, you can get up to 10 or more. And so if you've got that excess external input of iron, it's not limiting, but if you don't have that, it is limiting. And iron is the critical sort of limiting nutrient to many of these areas. Zinc, you need 1.6, you've got 1 to 3, possibly limited. But the thing about zinc is that there's some really nice work now where if they run out of zinc, they switch and use cobalt. If they run out of zinc, they can even switch and use cadmium. And they've shown now that cadmium can substitute for zinc in carbonic anhydrase and some of these enzymes. And so there are mechanisms that they've evolved to take care of that. But if they run out of iron, that's it. They're stuck then. So I'll show you a little bit of data along here. And to me, this is sort of my favorite area of the backyard, from Point Conception to Cape Mendocino.
I shouldn't interrupt, but just for any of you who eat algae, your point on cadmium, some of the Indian sources many groups have cadmium levels that are too high. And I think it's for precisely this reason. So we're very careful about the algae we eat. Sorry, Ken.
Yeah.
In all these measurements that you did, all those calculations, you all only consider the inorganic forms. And we know that there are some organic forms, both nitrogen, phosphorus, etc. What happens when you put that into the equation?
In these coastal upwelling areas, they generally, you're dominated by the inorganic nitrate, the inorganic phosphate, and everything. It's more when you leave the coastal upwelling areas and you go into the oligotrophic waters, then they really start looking, well, what kind of dissolved organic nitrogen, dissolved organic phosphorus might I have, and these other things. But we're dominated by the inorganic chemistry in these areas. Okay?
Thanks.
Yeah, for first order impact, it's this inorganic chemistry. Okay. Okay, so here's what to show you, just as an example to drive this home again, is a station here in Año Nuevo. This is the sort of upwelling center that Francisco talked about that sort of drives water into Monterey Bay here. Here we are. And then here's an area out here in this warm California current water. This is your sea surface temperature image with the warm water. Blue is your cold water. And so I'll compare this station with this station. And what you see is that warm California current water out here, and then the upwell water. And so you're really seeing this water being brought to the surface here with the temperature. If you look at salinity, you see the California current water is a low salinity, the upwell water is a high salinity being brought to the surface. You see the California current water has non-detectable nitrate, it's oligotrophic, and you see that 24 to 30, 20 to 30 micromolar nitrate being brought to the surface. Silicic acid, you're bringing enough silicic acid to the surface. And then iron. Here's what a typical offshore distribution of iron would look like. And if you just brought that amount of iron to the surface, you'd drive the system into iron limitation. But then you look at these areas near shore, and you start to see this sort of external input. And this external input is what varies remarkably depending on where you are in these coastal upwelling areas. And now I'm going to show you sort of a contrast, here's the Gulf of the Farallones, here's your San Francisco Bay. This is for the West Coast. For the West Coast, this is a very broad continental shelf for West Coast standards. And here is the Big Sur coast where you don't have a continental shelf really. Also, you've got major rivers coming in along here. You really don't have the rivers coming in along here. So you've got a narrow shelf without the river input. You've got a broad shelf with river input. And then if we look at what happens with surface chlorophyll during a short relaxation event following intense upwelling. So I purposely picked, we had a week of intense upwelling, then a short relaxation event, and a bloom. Okay? And so here's the whole Gulf of the Farallones, here's Monterey Bay, the whole Gulf of the Farallones, it's 30 micrograms per liter, a tremendous phytoplankton bloom dominated completely by diatoms. And then here's this area off of the Big Sur coast. You have the same amount of upwelling. You have the nitrate there and everything, but it's just not blooming. You've got these values down here of maybe 1 to 3 micrograms per liter chlorophyll. And this was some of the very first work on this. Was Dave Hutchins was a graduate student of mine at that time. And when we went out here into this Big Sur water, this upwelled water here, we looked at controls on shipboard controls, and they just sat there and did nothing. But you added 10 nanomoles of iron, and they just ballooned. And ballooned on a time scale of 4 days. Okay? So you have these, everything was perfect. So they're doubling at 2 per day, and just going boom, 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 boom. And in 4 days, you have this tremendous bloom. And without that iron, they sat there. And it's sort of a perfect explanation here for that water still being as blue as it is, or as light or yellow or green as it is. Up here, it already had high chlorophyll. Whether you added iron or not, it continued to bloom until it ran out of nitrate. And nitrate became the limiting factor here. And it bloomed a little bit more because it still had some residual nitrate. Once it finished up with that nitrate, that was it. But here, it had the nitrate. It had about 25 micromolar nitrate, but without the iron, and it did. Now, if we look at this in a little bit more detail, what you see is this is a California, here's San Francisco Bay, Monterey Bay, sort of the first clear day right after a winter flood event. And I just want to show you the sort of storm events where winter floods are bringing in a lot of particulate iron, essentially bringing in this mud. But the mud, this clay and silt-sized material coming here from the rivers into this area have iron coatings, and they're rich in iron. There's not very much dissolved iron in this. The iron is on the particles, on coatings on these particles. And a lot of this material then gets deposited along the mud belts along our shelf. And okay, I added this one because what I want to show you here is the daily mean stream flow. And you see the flood events are occurring in December, January, and the flood events are occurring in the winter in December, January. And you see here's a low flood event here, here's a really low one. But you see the flood events that are delivering this iron to the coastal ocean are there in December and January. And then in blue, what I plotted is the coastal upwelling index. And you can see that the upwelling is minimal in January and December, where all that iron is being delivered. And the upwelling is 6 months out of phase with when the rivers are delivering that iron. So what's critical is that the shelves, these mud belts along the shelf, are acting as sort of a capacitor and trapping those iron coatings and everything. And then iron is being released from these shelf areas to the benthic boundary layer. And that's one of the reasons I love Chris Edwards' benthic boundary layer importance, because as this water's coming up along that benthic boundary layer, it's picking up that iron from these broad shelf areas. And here's off the Big Sur, you just don't have the shelf, and you don't have the rivers, and these things don't have the mud belts. And so here you've got now the water coming along without getting the iron into it. And so along the Big Sur coast, you're getting the nitrate, the phosphate, the silicic acid without the iron. But along these areas of the broad shelf, you're just supplying that iron all the way along that sort of benthic boundary layer as it's coming up. And now you're supplying everything you need. And now you get these extensive blooms of large diatoms. And here you get an HNLC area without the blooms. So you've really got to be careful which area you pick. If you wanted to try and do a phytoplankton bloom and you're taking water off the Big Sur coast, good luck. Unless you have awfully rusty pipes or something like that, and adding a lot of extra iron. On the other hand, if you wanted to do this in another area over a broad shelf within mud belts, then you've got it. Okay? So looking up and down the coast, you see there are these areas. Here's the Gulf of the Farallones, and it's a broad shelf. Up here north of up here by the Eel River coming in, the Russian River, it's a broad shelf. Here up by Año Nuevo, it's a narrow shelf. Here we've got our narrow shelf. Here we've got another sort of broad shelf. So if you look at a image, this is an average for June this is a June image for a monthly image. I just want to show you how well sort of this works out when you take a look at this and look at it in more detail. Along the Big Sur coast, you see the chlorophyll images, you know, the chlorophyll concentration is sort of this 1 to 3. It's got the nitrate, it's got excess nitrate, it's got excess phosphate, excess silicate. It just doesn't have the iron. It's trying to bloom. It's blooming much more than the oligotrophic waters offshore that don't have the nitrate, don't have the phosphate, don't have the silicate. Here you've got the nutrients, but you don't have the iron. Sitting there trying, it just can't do it. But these areas here with a broad shelf, where you're adding that iron from that benthic boundary layer, there you see it's blooming, here it's blooming, here it's blooming. So every area along here where you had that broad shelf supplying the iron, you see it standing out as major diatom blooms, 30 micrograms per liter or more. All these other areas, it's sort of trying, but not quite able to.
What happens off Oregon? You still have a shelf and you have rivers, but you don't have the blooms. In that image.
Huh?
In that image, you don't see the
Let's
blooms
see.
in that image.
Up here?
Yeah.
I have to look at an image all from here to here you had upwelling. Okay? Here you did not have, in the Southern California Bight, you did not have upwelling during that month, and so you had lower productivity there because you didn't have upwelling. And I think up here you're getting lower productivity in that area because you didn't have upwelling. Whereas along this stretch here you had the upwelling, and that's what I had focused on. Okay?
Hey Ken, if you looked at dino blooms, would it be the same?
No.
Okay, so this is.
Well, and I'm not going to. I'm a diatom guy, okay? And so dino blooms will often are much more localized, will often come in after the diatoms have had their day and everything else.
But they still are high iron, or they have iron requirements.
They have iron requirements, but they have all kinds of tricks that they could use, just like they have for the nutrients, you know, where if the diatoms are done and have had their day, then the dinos can come and migrate and pick up things that way.
Yeah, but they would show, it's messier, but they would show limitations.
Yeah, but in all of these cases where you had everything you need, where you had the nitrate, the phosphate, the silicate, and the iron, and the zinc and everything, it was diatom blooms. Okay. Right? Okay? Yep.
Although if I can tag on to Mary's question, when Charity sees dinos in the ponds, you see them the most after a fish kill, would you say, Charity?
Whenever there's a lot of organic stuff hanging around.
A lot of
There's been a
organic.
big bloom that wasn't taken care of by,
In the ponds,
yeah.
got long residence time, so they're,
Yeah, and more towards the end of the summer when the salinity's a little higher.
Okay. So I'm going to touch right now a little bit about sort of the mechanism by how you can get iron into the benthic boundary layer. And so these mud belts that you see in the shelf areas are very organic rich, and within a few millimeters of the surface, and centimeter for sure, you see them going anoxic in the sediments. And when you see that happening, what's happening is that the iron-3 and these iron coatings, iron-3 is extremely insoluble. And just by itself, the inorganic iron-3 chemistry, we would have about 1/10 of a nanomole of iron in the oceans, okay? But iron-2 is extremely soluble, and you get hundreds of micromoles of iron-2. But iron-3 is extremely insoluble. And so, and it is on these coatings that have those particles and everything, but when you get this reduction in the sediments, you get hundreds of micromole of iron-2. Hundreds of micromole of iron-2, that's hundreds of thousands of nanomoles of iron-2 in the sediments. And it's diffusing out. In those areas along our California coast, where we've got lots of oxygen in the bottom waters, that iron-2 is oxidized up to iron-3 in a matter of, say, minutes, tens of minutes kind of time scale. And it's oxidized to iron-3. Now, if iron-3, if it wasn't for this red L1, that iron-3 would only build up to maybe a few tenths of a nanomole in concentration. It would all be precipitated back on the particles. But because of this L1, and these are organic ligands that are really strong iron-3 chelators that chelate the iron-3 and hold it in solution, you get high concentrations of iron-3 in this organically complex or chelated form that can exist. And diatoms have evolved to be able to access that form of iron and readily access it and use it. And also these ligands can also help solubilize some of the particulate iron that's there too, that might just be resuspended from the shelf sediments as well. And so whatever way, whether it's this iron 2 mechanism or whether it's just resuspended shelf sediments, you get these ligands that are acting to solubilize that. And the bulk of the iron in these coastal waters and these benthic boundary layers and upwelled into the surface is in this form. And essentially, it's a concentration of ligands that sort of caps the amount of iron that you could have in solution. These ligands are almost titrated with iron to then get this form. And that here's this is a busy one. I'll just sort of show you real quickly. Here's Chris Edwards' picture of the nitrate being delivered along the benthic boundary layer up into these areas when you got the right, what's that number, that S value?
Burger number.
The Berger number. When you got the right Berger number, you get the nitrate coming up along that benthic boundary layer. As that nitrate's coming up along that benthic boundary layer, you're picking up iron. And so here you've got that 30 micromolar nitrate coming up along here. This is this, it's not in focus really, but this is that 30 micromolar nitrate that's in this figure coming along here. And as it goes along this benthic boundary layer, you're picking up and adding up to 30 nanomole of iron to this. And the reason you're adding that 30 nanomoles of iron is because of these ligands that help solubilize it. And the gray line I put in here is sort of the iron to nitrate concentration that you would need to get these extensive blooms of large diatoms. And so you're above that, and that external source of iron into the system has brought you above that to where you're adding enough iron to go along with that nitrate and silicic acid. The red dots out here are the offshore wind curl-induced upwelling that occurs offshore, or in these cyclonic eddies. And out there, offshore, you're not bringing up anywhere near enough iron to go along with the nitrate, the phosphate, and silicate. Okay? And this is going to factor in because if you try and do an offshore upwelling experiment, you're going to be upwelling that amount of iron with the nutrients, and you're in trouble if you want to put a plant, if you want a diatom boom. Okay? You got to get this. You got to get your upwelling coming from sort of the benthic boundary layer like this, and then you've got it. And here, this is sort of the ligand concentration versus iron. And it shows you never do we see an iron concentration greater than the ligand concentration. Usually we see about, the ligands are about 90% titrated with iron. And then we see that being utilized as well. Okay, so conclusions for this part is that coastal diatoms require a substantial external source of iron to grow at optimal rates. They need the external input. They can't get along with just the internal iron coming with the upwelled water. Comes from these, it comes from the mid-shelf mud belts that act as sort of this capacitor. These iron-binding ligands play an important role in solubilizing it. And these iron-limiting upwelling regimes can exist in coastal upwelling regions that have a narrow shelf and a limited river input. We've done this area work off of Peru, and the southern Peru coast has a really narrow shelf, and we see it building an iron limitation just like that. The northern Peru area that Francisco told us all about is really productive. It has a broad shelf, tremendous iron input, and there you get these tremendous blooms. And in fact, I'm going to move ahead here and show you one more thing here. That we've done some work. Maeve Lohan and I wrote a paper that came out recently in Environmental Science and Technology. And we were interested in up off of Washington and Oregon that have shelf waters that have recently become hypoxic up there. And so this is area, and this is a paper by Chan and all in Science in 2008 showing you that these sort of hypoxic shelf waters have taken place. So this is 2006, where you got this really low oxygen occurring over the shelf, over the mid-shelf area. And so we were up here in 2007, the year after that, and looked at the Washington and Oregon coast and looked at the shelf here, 100 meters up here to the surface, and looked at that really low oxygen region occurring. Now it's not suboxic yet, it's not denitrification, it's just hypoxic, low oxygen. And hypoxic, the definition, it depends on what your favorite organism is. If you're a crab fisherman, then you have a value of hypoxia that limits the crab's ability to move into that area. If you're a squid person, then it's a different value of oxygen where you claim it to be hypoxic. So it's just lower oxygen. But that low oxygen and that colder water, a combination of, there's sort of a couple things that act on when they, I'm sorry, I forgot. When the iron 2 diffuses out of the sediments into the benthic boundary layer, off of California, it oxidizes in about 10 minutes. But off of Washington and Oregon coast, the three things that act on it are temperature, oxygen, and pH. And it turns out that these are very cold, 7.5 degree water, very low in oxygen, and also for that same reason, they're very low in pH. And what it did is it increased the oxidation sort of half-life of iron 2 to about 12 hours instead of 12 minutes. Okay? And so now that allowed the iron 2 concentration to build up to much more higher levels. And iron 2 is a very soluble form of iron. And so what happened was that in this area, okay, in this area here, we saw iron 2 concentrations of 18 nanomolar. We're off of California, there wasn't any. Iron 3 was 15 nanomolar, comparable to this 10 to 15 nanomoles we see off California. And that sort of doubled the amount of iron that was in this benthic boundary layer that was being added to the overlying water. And it's sort of a positive feedback in a way that once it went hypoxic, we doubled the amount of iron in the benthic boundary layer and doubled the amount of iron provided to the surface waters, and then enhanced the blooms even that much more. Off of Peru, the water is actually suboxic. So you've got denitrification, and the oxygen level is so low that you actually can build up really high concentrations of iron 2. So this is a concentrations of iron 2 we see in Francisco Chavez's area of Peru. We see these values of 40 to 100 nanomole of iron 2. We still see some iron 3. It just slowed down the oxidation of iron 2 so much until it upwells into the surface waters. But this is an area that has, you know, that not only you're upwelling all that phosphate, nitrate, silicate, but you're upwelling a ton of iron to go along with it. And man, those phytoplankton off of Peru have it made, you know, and so it's a tremendously positive sense, you know, in that area.
So another hypothesis then to add to the list of why there's so many fish up Peru.
Yeah, because this will drive the biggest, juiciest water diatoms imaginable. The blooms are the really big ones because there's just no limitation at all.
Then is the anoxic, this is all happening on the sediments, right?
Yes.
In the water column is a low oxygen,
Though,
providing iron as well?
no, from what we see, manganese will go into solution under those suboxic conditions, but iron requires anoxic conditions to go into solution.
But it is anoxic.
It's an anoxic.
No, once there's been a couple cases where people have had evidence to go truly anoxic, you've got to have hydrogen sulfide, and it's got to be based upon sulfate reduction. And off of Peru, it's suboxic. It's based upon denitrification. That's suboxic conditions.
Not necessarily. Basically, when we have used stock sensors that shows us that there is no oxygen, and maybe there was a paper not recently talking about the cryptic sulfur cycle, where you can produce maybe and you can remove.
Okay, but in many of these cases, now that they're measuring oxygen at the nanomolar concentration, they're with these extremely sensitive oxygen probes, they're seeing oxygen at these very low levels.
So 10 nanomolars is enough?
Huh? Yeah,
10 nanomolars.
yeah, to keep it suboxic.
Yeah.
Yeah.
And so, but when you measured it in the water column, or did you?
Yeah.
On the Peru?
Yeah.
You didn't find the same, you didn't find high concentrations in the water column?
No, this is water column.
But that's close to the benthic boundary, or is it in the surface?
No. Then once it's in the surface, we see the really rapid removal as it's luxury uptake and everything else, you know.
But if you went off the shelf and you made a profile, you would never see the 40 to 100.
No. So if you've got wind curl induced upwelling offshore, you don't see this. This is this coastal upwelling.
That's what we claimed in the review that we wrote in 2009, that it wasn't the size factor that, I can't pronounce his last name, Czech student.
Yeah.
Well, now, what was the significance though? We have seen hydrogen sulfide in the water column.
So when I've looked, you see, maybe once every 12 years, there's somebody reports maybe seeing some evidence of hydrogen sulfide in the water column where the Peru, subsurface waters off Peru have gone anoxic. But the majority of years, it's just poised. a third of the way through denitrification. There's still 2/3 of nitrate left. It's gone a third of the way through denitrification. To get truly anoxic, the nitrate's gone to 0 and it's
Then
converted.
it goes out to sulfide.
Huh? And then you get sulfide.
We've seen that in water
But
column.
1 year.
Well, yeah.
Okay, out of 12, I mean, or whatever, or 15, have you, I mean. Okay.
It's
In
not,
most-
it's
What I was trying to get at, what is the consequences for iron in the
Well,
in a hydrogen sulfide environment?
well, to me, as long as there's nitrate left, the system is poised on denitrification, and where they're taking the nitrate, you've got denitrifying bacteria that are doing their thing in that subsurface waters, okay? And that's the most critical thing, and there's just and most people who try and measure oxygen will see just that tiny bit of an oxygen still there, okay? In some cases, for, especially during maybe these La Nina events, that the system can go through denitrification and into sulfate reduction, where you get hydrogen sulfide. And that can happen some years, but looking through all the literature, I've sort of seen that happen once, and all the other times it's poised on denitrification.
Yeah, that was one of the big questions that we had when we started our Agron program, was if we don't see hydrogen sulfide, it's because we are not measuring 0 oxygen, and if we are measuring why it's not going to 0. That was one of the major questions. Now, every time that we went out there with these ultra-sensitive sensors, basically we went down to basically 0. We didn't see any signature in our stock sensors, suggesting that yes, there was still nitrate, there was still denitrification, but that there was denitrification, but we couldn't see any oxygen in the system.
So what sensors were you using?
Stock, the stock sensors, the ones from
The ones from Scandinavia? From
the Scandinavian
Oh.
one, yeah, with
Okay.
yeah.
I
So-
still define things on denitrification and full-blown sulfate reduction, but
Yeah.
you might find a picomole of sulfide and say that it's okay. I don't know.
Yeah,
Okay.
just to make the point that we didn't see
Okay.
any.
But what's fascinating for us as fish farmers is, man, we have hydrogen sulfide in the bottom of those ponds.
Yeah, especially coming from the sediments, or if you let the ponds go anoxic.
We weren't trying, I mean, the farmer was madly turning on his
Yeah.
paddle wheels in the
Yeah.
summertime, but
Especially you get these organic-rich fish ponds and
It-
stratify them, and you can really drive these
the
systems.
wonder was that the
Yeah.
fish survived.
Yeah. Okay. Oops, excuse me. Let me go backwards here.
I have a question.
Yeah.
What happens to iron when you do get a completely anoxic situation?
Oh.
You get hydrogen
That's
sulfide.
what-
Then the iron goes sky high.
That was my question.
Yeah. It goes, and then you start dealing with pyrite, and any iron sulfide precipitation, but the iron still gets really high, micromolar concentrations, not nanomolar.
And so what happens to the algae population?
Well,
There's no oxygen, so they can't.
The only place that we really have that occurring is places like the Black Sea. And the anoxic waters of the Black Sea are so deep, way below the photic zone. Okay, and then the iron fluid diffuses up into the suboxic region, where there's denitrification, and then it diffuses up in the oxic region, and it all is precipitated out there, and then settles back down. So you get this tremendous recycling. So there in the Black Sea, it's so well stratified, you're not upwelling that water to the surface along these benthic boundary layers like we are in the coastal upwelling areas. Okay? So it's precipitated out subsurface
Right.
below the photic zone. And then what happens is really neat. It diffuses up, precipitates out, gravity acts on it, sinks back down, is re-reduced, diffuses up, precipitates out, gravity acts on it, sinks down, and you get this tremendous recycling effect right at the oxycline, the redox cline.
So Ken, what are the phytoplankton that dominate under those conditions?
Well, they don't, I mean, under those conditions, we're talking about places like the Black Sea
Yeah.
and it's below the photic zone. Okay. They
But
never
it's
made
not-
it.
But it's stable.
It's stable, but it's, the redox cline is deeper in the water column. And what I'm saying
Oh,
is
I
that
see. Okay.
I'm talking about in these areas off Peru and the all through the eastern tropical Pacific, you've got this suboxic water mass over the shelf. that puts in a lot of iron, keeps it stable, and then you get it upwelling along the benthic boundary layer, and into the surface, and now you're providing all of that iron together with the nitrate, the phosphate, the silicic acid. And so now you've got a mechanism to get it up into the photic zone, and that's the coastal upwelling along the benthic boundary layer.
And this benthic boundary layer thing, has anybody ever observed that? No.
Okay. You don't,
observe.
maybe you don't need that.
Upwelling along, you don't need the benthic.
Okay, you don't, you just make upwelling and mixing of
I
that
don't
deeper
think
water
you-
that's in that deeper water up over the shelf, up into the rock.
One of the things that it was in the, around 2000, going back to your question, I think it was Ripida, and then we saw it from Chile and Peru, and also from Mexico, where you have the hypoxia. I would call it hypoxia, I would not call it anoxia, but it goes into the base of the euphotic zone, and in those regions, when you have very low oxygen and you still have light, what we see is Prochlorococcus, where you have a peak in Prochlorococcus, and it's basically a monoculture of Prochlorococcus developing in those. You have no oxygen, you have light, and Prochlorococcus forms a secondary peak of fluorescence. It's a beautiful.
Yeah. Yeah, I mean, you would predict that either a cyanobacterium or a floatal organism, like the manoflagellum, would dominate under those conditions.
There's a stable Costa Rica upwelling dome that you see that same sort of thing.
Yeah.
I was going to ask, what kind of geological formations do you have iron associated with upwelling? Like seamounts? Is it deplete of iron, or
Well,
do you have any idea other than these near shore broad shells, coastal broad shells?
I mean, here the Galapagos Islands are in this, in the equatorial HNLC area, and you can see the bloom around the Galapagos Islands from that. Here the French Marquesas are in this HNLC water. You see the bloom of productivity around the French Marquesas. So you see this happening everywhere you look. You know, here you see, anyway, you can see these islands right here. The French have done some really nice work on these islands right here. And that's an HNLC area in the Southern Ocean, and you see it blooming around those islands. So the volcanic islands are putting in iron as well, okay? But it's the, you know, it's, now I'll go backwards. There, this is the one I want. So here is sort of the best model that exists right now by Jefferson Keith Moore at UC Irvine and a graduate student at his Boucher in 2008. And they put together both the iron from dust, from the dust input, and the iron, the first attempt at putting in iron from sediments. And it's a little hand wavy, but that was their first attempt. And you see, I mean, the thing that really shows up is the Sahara Desert dust event here. And this is an exponential scale here, okay? So it's an exponential scale. And you see this phenomenal amount of iron put in here off the Sahara. And that's what allows John Zayre's nitrogen fixation to occur here in this area. That's what's depleted it to where it becomes phosphate limited here. This is one area of the ocean that's phosphate limited because you get enough iron put in for nitrogenous to play a role. But these areas up here, even though there's a fair amount of iron put in the subarctic Pacific, there's so much more upwelling in that cyclonic gyre of the subarctic Pacific that it overwhelms that and still becomes an iron limited area. The equator is an iron limited and the Southern Ocean is an iron limited. And then here is the shelf, sort of, it's from the sediments less than 500 meters. And here you see the Bering Sea, you know, is this iron-rich shelf, broad shelf area with all that iron being recycled and put in. But I want to add, you know, the beauty of this model again is that it shows you, you know, Francisco Chavez's region of Peru here, where you've got that shelf. You don't have, there's very little dust, but you've got the shelf source of iron, the external input of iron that's required to get that system to be as productive as it is. And then, okay, and then
Francisco, are you laughing at the idea that that is your show?
We'll call it the Francisco show.
We all want to be his best friends.
Okay, and now I want to finish with one last thing, and this is this discussion question idea and everything. And So here are our coastal upwelling regimes. This is the Chile, the Peru, you know, the Oregon, California, Baja, here's our Benguela, and our South Africa. And if we look at the tropics and we look at these areas like Peru that have suboxic water beneath the surface waters that Francisco showed earlier, that was sort of item number 3, that the suboxic waters, subsurface suboxic waters were keeping the zooplankton all up in the surface and keeping the food there for the, and also all the diatoms were in the surface, they were so productive, and so the anchovies were just grazing away like crazy. There was no vertical migration allowed in that area, and that's one of the reasons that Francisco thinks that this could be a really, you know, is such an efficient area at allowing fish production. And also, it's sort of slow, gradual, continuous, all these things that you wanted, instead of this eddy-rich, much more energetic area of California. A similar area to this can be found right along here at 15 to 20 degrees north. You've got suboxic waters. It's the eastern tropical, you know, it's the eastern tropical Pacific, but the northern part of the eastern tropical Pacific. You've got suboxic waters at 50 meters depth. Below it, iron-rich waters right there. But the trouble is it's oriented the wrong way. So the winds are blowing sort of from north to south there, and you don't get the upwelling, coastal upwelling winds. It's oriented the wrong way, and it's just not turned on. Over here, the same latitude over here off Benguela, the winds are blowing the right way along the coast parallel. It's turned on, going. But this one area here just isn't. And I think if I go backwards now, here. So then I took this out of this paper by Pennington, and Francisco's a co-author on that paper in 2006. And if you look at sort of 5 degrees south to 20 south, this is Peru. This is coastal boundary along the eastern margin. And this is this productivity or the biomass that occurs here along that South Pacific. And then here's this area 15 to 20 degrees north that I just showed you, and it's just not high in chlorophyll at all. And then you look at these other figures that were in that model, in that paper. This is this area I'm talking about right here. The Gulf here has these winds that are coming down through the mountain valleys and everything else and make it much more energetic and much more variable. But this is an area with just nice, uniform, constant winds again, but they're slightly in the wrong direction. You know, they're coming from the north, not parallel to the coast. And you look at the chlorophyll through that whole area, and if I was going to pick any area in the world that would have the closest to Peru sort of conditions, it would be a turn-on upwelling in that area right there. The only trouble is it's a very warm area there, and you make it colder. There might be a coral reef there that you'd get into trouble with messing up or something else. But that would be the area that would be analogous to Peru that you could turn on, and you'd have everything you need. You'd have this, and you'd only be pumping it up. The other thing I put in here, I'll go back. Yeah, I put in these figures here, right here. You know, all along here you've got that high nitrate at 200 meters, you've got that high nitrate at 100 meters, you know. You only have to go to 100 meters depth and pull that up from the benthic boundary layer where you've got all the iron as well. And now you're turning it on. So out here, you got to go to 500 meters to get that same nitrate. Here, you go to 100 meters, you've got it. So anyway, I'm leaving that with sort of a controversial...
well, all you need to do is negotiate with the Mexicans.
It happens to be right off southern Mexico.
The drug cartel.
Yeah, the drug cartel.
Well, it's also an area where you get a lot of tropical storms and hurricanes.
Yes,
yeah. So maybe the wild idea I just came up with can be shot down in a matter of seconds.
Excuse me, I love your wild ideas.
Anyway, and so this last slide I didn't go through. It shows the oxygen. This is a really oxygen depleted water there that's goes suboxic that will lead to enhanced iron input. That's all. Over the coast, in the coastal upwell, not offshore. And if you try and put one of these systems out at Hawaii and you're away from the island effect, you're going to have to go really deep to get that same amount of nutrients, and you're going to get no iron, unless you got really rusty pipes. and you're going to have problems. So be careful where you locate these things. Okay? Yeah, Hans.
Ken, you were, when you first started your talk, you were talking about sort of timescales of 100 or so years.
Yeah.
For the, have you done a calculation of anthropogenic iron enrichment, and does it ever catch up?
Some of the modelers are trying that now. One thing we know,
What's the anthropogenic enrichment?
well,
The dust and pollutants?
yeah.
Well, additional dust because of what the certification?
No, it turns out that
Yes.
that anthropogenic dust from
Land use.
you know from different sources.
Yeah,
The
those are
iron,
sources I was wondering.
the iron is more soluble. So the iron coming from the Sahara Desert, it's only 1 or 2% of the iron is soluble, but there's so much dust coming from the Sahara Desert that is really important. But the iron coming from sort of anthropogenic aerosols, anthropogenic dust, can be 10 or 20% soluble versus 2% soluble. And so it's more than an order of magnitude, it's more soluble. So an order of magnitude less anthropogenic dust can have, can have an important effect.
And so is that coming out of burning of fossil fuels?
Yeah.
So is there iron in the fossil fuels?
There's some, and they remain, and I'm not sure anybody's really, the measurements have just been made recently, the papers have just been written explaining that this anthropogenic dust is more soluble, and now the modelers have to try and put it into their models. And maybe we'll start to see a bigger signal coming from China across the Pacific.
The inverse has been considered too, right? If we start to grow crops in the Sahara,
Yes.
then we would reduce the source
Yeah.
of iron, which would cut global primary productivity down.
Yeah, they see tremendous changes from droughts and everything here. In fact,
Actually, there were a couple of nice papers about China's contribution to iron and how it changes with droughts and the source of iron.
Yeah.
depending.
but these coastal upland areas along the eastern boundaries, these are the areas that are primed, and they're all far enough removed from China that you're not going to get that much dust there compared to what you need as an external input. We've got to look to the sediments, and especially if you've got sediments where you've got suboxic waters or overlying them, or hypoxic waters overlying them.
The other place where you would still need dyed iron that has a shallow nutricline is the Eastern Pacific in general. But the problem with getting away from the coast is the fact that you would need to add a bunch of iron in addition.
Yeah, exactly. So there's
But because there is a shallow nutricline all along
Yes.
that Eastern Pacific.
exactly, but you're going to have to somehow add that iron, and the iron disappears very quickly. And so you got to have, it'd be a very expensive proposition if you're trying to add iron. Even though you only have, you've got like, for the coastal diatoms, you've got, 20 micromoles of iron per mole of carbon, that kind of thing, so it's or 30 micromoles of iron per mole of carbon, these coastal diatoms is what you need. So you need 30 iron atoms per million carbon atoms. But because we're dealing with the scale of this, you still got to add a lot of iron. So what you want to do, you don't want to get into that. You want to get into a place where you're bringing everything up perfect for the diatoms bloom. And where you don't have to add any phosphorus, you don't have to add, that's going to be really costly, you don't have to add any iron, that's going to be really costly, you don't have to add anything. Yeah.
The boundary layer, which has become famous today, is
influence.
It exists because of equatorward winds. So, just thinking about your position off of Mexico there, that may be an area where the sediments are primed, but the circulation is not actually. There is no bottom boundary layer there because there is no upper. It's very weak, and there may not be a ready source unless when we're mining the sediments in some way and stirring up the pore waters or something like that.
Well, there's always a bottom boundary layer, but it's not necessarily a bottom boundary layer as being important.
That's true. There is always a diffusive layer.
Yeah.
One beautiful place where you have constant, pretty much blooms in the open ocean and where the Spaniards tend to keep fishing all the time is the Argentinian
Yeah, yeah.
Patagonian. That fish there is
This is,
Wild shelf.
yeah, wild
yeah,
shelf.
this is a wide shelf acting as a nutrient trap. It's amazing, and you've got a lot of iron dust coming in, and you've got a wide shelf that provides the iron. It's a nutrient trap. It's a phenomenal
It's a
productive
phenomenal
area.
productive area.
Yeah, yeah. And then this area right here
Yeah.
is because of the island effect, you know. And there's the Galapagos, and there's the French Marquesas, you know.
What's that big blob south of the Marquesas there?
Oh, you know, I'm not sure. This is Keith's, I'm not sure.
Jefferson.
I'm not sure.
Ken, I had a question about the iron dilemma, which we both worked on, which is you add iron and you may grow toxic algae.
Oh, yeah.
So, which would not be a good iron.
So, what Mary,
But, yeah, so could you say a little bit,
I'll
because
say a
that
little
would
bit.
be a balance of
Yeah.
nutrient.
So Mary was the first author in a paper, and then there's another paper that deals with this issue too. And it turns out that in 8 out of 9 of the iron enrichment experiments that were done in the Equatorial Pacific, the Subarctic Pacific, the Southern Ocean, it was diatoms that bloomed. But in a number of these, it was pseudonychia, these chain-forming diatoms, pennate diatoms, or pennate chain-forming diatoms that bloomed. Not in every case, but in most of them, it was these chain-forming pennate diatoms that bloomed, pseudonychia. And in the paper that Mary was the first author on that was just published recently, they showed evidence that they were also producing domoic acid. And so it was an example of a harmful algal bloom that took place in these iron enrichment studies. So that's one of the things that one would have to be really careful about. And it turns out that I really think that Adrian Marchetti has written some really nice papers showing that these pennate diatoms really have an advantage to be sort of that background milieu of diatoms that are there waiting for repulsive iron. And they also have the advantage that they can take luxury uptake of iron, store it as ferritin, and then pass it on to their progeny. So that they're just primed to take advantage of any of this. And the pseudonychia is, and so they're the ones that we see oftentimes these open ocean iron enrichment studies. I'm not sure that in the coastal upwelling areas that we're gonna, I mean, they're there, but we're dominated by these other diatoms that are the quote good ones, you know, and not the harmful ones.
But we have to be
But we have to be awfully careful, especially about pseudonychia producing domoic acid, you know.
That would look ugly.
Yeah.
My pseudonychia could be that it has something to do with what is the form that iron is added experimentally that leads to pseudonychia versus something else. Yeah. I mean, in other words, the chemistry of the iron that's in the sediments may not be the same as the chemistry of the iron that you add in a manipulation experiment. Where is it?
Actually,
Well,
The background,
ginger does a lot of them.
the background concentrations of diatoms in the open ocean tend to be these smaller pseudonychias, smaller ones. I wonder if they actually
They
have.
do
diff-
produce toxic dominant.
No, but I wonder if they have like, if once they get iron, they get bigger.
yeah, Adrian has shown that
Because they would be the.
without iron, they're really skinny and small and really skinny, and so they increase the surface area to volume ratio, your biovolume. And then with iron and nitrate and everything, then and silicate, then they become, they change their aspect ratio by triple, so they become much wider
Oh,
and a bit
yeah,
longer.
because those are, Kurt has counted throughout the globe, and the 5% of the diatoms that are in the open ocean are all little pseudonychias.
Yeah.
Mhm.
They're-
Yeah, there's a
So that's
lot
why,
everywhere.
that's why they,
That's
Yeah,
a little scary.
and
the background, well, there may be, there is still centrics out there,
Yeah.
but there's a lot more pseudonychias than there is,
But in these upwell areas, what we want are these big centrics, these pizza, family pizza style these chain diatoms and stuff like that.
yeah, so the open ocean
Yeah.
diatoms are all toxic.
Probably.
Yeah.
So you don't want to grow.
It's a fact of life.
Yeah. Yeah, so that's another reason why it's a coastal upwelling unit. So
Right.
are primed for enhanced diatom productivity, enhanced
What's the
fisheries.
evolutionary reason for that is?
Well, I think you described it. They can maximize their surface area relative to centrics.
And,
But why be toxic in the open ocean and not so much near the coast?
Well,
No, they are.
They're
They are.
very
Yeah,
toxic.
and they're not always toxic. They can turn on their, and there are lots of hypotheses as to why they're
Yeah.
producing this. One of them
Yeah.
is grazing.
I-
The other one is to capture iron,
Yeah.
right?
See, I
But I didn't mean, I'm sorry, I didn't mean that the pennates and the pseudonychia wasn't toxic or non-toxic. I just meant that the centrics
Oh.
are closer to the coast. The pennates tend to
No, but-
hang up.
No, the pennates are also along the coast.
Also
There is
along
a
the coast.
succession. So that they, for example, here, they tend to come,
In
be very
March.
important later in the year, actually.
But we noticed here there was a pseudonychia bloom. We came down to Moss Landing, David Kingsbury and I, 3 or 4 years ago to talk with Ken Cole. And there was a pseudonychia bloom right then, right there.
Yeah, but
And it was
but on average, their average distribution is to have a peak right after this centrix, and so there's kind of a succession of from centrix to pennates to diatoms, and it's those last two that have been the ones that have sort of been increasing over this regime shift.
So back to my original question, what's the evolutionary, why do you suppose centrics and then pennates?
According to Margalef, it was because for the centrics and the pennates, it's a little harder to explain. It was a growth continuum, right? The diatoms, really fast growers, high nitrate. The pennates are sort of intermediate. They can handle they don't need to shift up maybe as the centrics do.
There's also,
They can handle middle to.
There's also, if you've got a wealth of nitrate, a wealth of phosphate, a wealth of silicate, and a wealth of iron, there's no diffusion limitation. And now you can have the large centrics growing and doubling really rapidly. As soon as you run out of as soon as the nutrient becomes limited, then you become diffusion limited, and then you win by getting smaller and smaller or long and skinny. And you increase your surface area.
Because
getting long and skinny
rhizosphere
or-
the
smaller.
centrics and
Yeah.
I mean